A big thank you to the Talk Python team who sponsor this episode of the podcast. If you want to get better at Python, now is an excellent time to take an online course. Whether you are just learning Python to delve into great topics like artificial intelligence, or you need to go deep into things like APIs and async, my friends at Talk Python Training have a top-notch course for you. Visit talkpython.fm/mind to find your next level and get a 10% discount. Also a big thank you to all my Patreons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience and other interesting topics to educate, inspire and engineer people's minds all around the world. I'm your host Joseph, and for this episode of the podcast I'm very excited to have the two founders of FIFTY2, Jens Cornelis and Markus Ihmsen, on my show. In 2015, after 8 years of research and achieving his Ph.D, Markus, together with his research colleague Jens, founded the company, which is a constantly growing startup and a think tank for world-class researchers and engineers. The company's vision? Transforming the engineering process, allowing to craft sustainable, more innovative and safer products at lower costs while pursuing the boundaries of simulation possibilities. The first product, PreonLab, is a particle-based simulation software for free surface fluids, which is unique in its ease of use, high performance and visualization capabilities. PreonLab is productively used by more than 50 companies in 12 countries. In this podcast, we will discuss where the smooth particle hydrodynamics, short SPH method, comes from, what advantages and limitations it has, why it is suited for easy parallelization, how it is validated, but also how engineers can use PreonLab for their purposes, and why the integrated post-processor and renderer can be leveraged for your purposes. And now, ladies and gentlemen, here's my podcast with the two founders of FIFTY2, Jens Cornelis and Markus Ihmsen. Okay guys, first of all, welcome to my podcast. It's really a pleasure to have two experts in the field of SPH on my show, so it's really nice to have that. What we also want to start with is, before we jump into the history of SPH, maybe each of you can give us an introduction to themselves. Maybe Jens, you can start if you want.
Yeah, hi there. Welcome everybody. Also from my side, my name is Jens Cornelis. I'm one of the founders and managing director of FIFTY2. I started my career actually as an apprentice at an insurance. And after a couple of years working as a sales droid, I made up my mind and studied computer science in Freiburg, where I met Markus. And I've been focusing during my research at the university on the field of particle-based fluid simulation.
Great. Markus, if you want to continue.
Yeah, thank you. So my name is Markus Ihmsen. I'm the other co-founder of FIFTY2. I met Jens at the university during my Ph.D. studies on computer science with the research topic SPH, which I learned about when I was doing my master's studies. Actually, my master was focusing on AI. I wanted to be an expert in machine learning. So still there is really a hype about, but I was dragged to physically based simulation, which I fell in love with. Because in my spare time, I liked to go surfing. And so fluid simulation had like combined my hobby and my passion with my future profession, actually. And there I am now, as working still in the field of SPH, but having dragged this from university to the industry, which was the right decision. Yeah. Mm-hmm. And at FIFTY2 now, I'm responsible mainly for the product development and working also as a managing director.
Mm-hmm. Excellent. For those of the listeners who are not familiar with SPH, could you maybe quickly explain what is SPH, what does it stand for, and how is the history of SPH? Because it's not a very young method, I would say, in my personal opinion. Maybe you can go a little bit into depth there. Maybe Jens, if you want to start, and then Markus can add some additional points.
Yeah, I'll do my very best. So actually, SPH stems from the 70s, and it was originally developed for the field of astrophysics. So to get information about how, for example, the flow of mass, of airflow mass on Mars, for example, is happening. And it was adopted for other applications later on. So for years, it was mainly used in animation industry, for example, for movies. This is also where we came from. But nowadays, it also plays an important role in engineering. And so compared to traditional methods that are commonly used in the world of computational fluid dynamics, SPH is a particle-based method. So the simulation domain is not discretized using a grid, but the fluid itself is discretized using particles. And from my point of view, SPH then is more or less an interpolation method. So how can I compute the spatial derivatives of the fluid of this particle distribution using an interpolation method, where now SPH is a kernel-based interpolation method, making this possible.
Mm-hmm. Markus, do you want to add your 2 cents here?
Yeah, please. So the term stands for smooth particle hydrodynamics. The particle part was well explained by Jens. Funnily, I think hydrodynamics is in there. Originally, the method was developed and is still used for astrophysics simulations, so really large-scale simulations. But it can be also used, like, for example, to simulate hair and non-hydrodynamic stuff, actually, which is pretty interesting. And as Jan said, it's in our opinion, and it's a mathematical interpolation method which helps you to compute spatial derivatives and other things that you need when computing these different materials on an arbitrary set of points. And it's thereby really similar to finite element method. I think they're inheriting from this the same idea, but finite element method uses then pre-computed weights, and therefore if the structure changes, then you need to adapt these weights, and this is done in SPH on the fly. Yeah, and finally the hydrodynamics part. So very often SPH is confused with a specific solver formulation. And this solver formulation was already introduced in the industry years ago and was not very successful. And so we have, in our research part, tried to overcome a lot of these issues. Yeah. And this is currently building the core of our product, PreonLab.
Mm-hmm. It's very good that you mentioned PreonLab. Before we jump into the tool itself and also the rendering part, could you explain maybe the advantages but also disadvantages and maybe limitations of SPH per se? What would you say? Whoever wants to add his 2 cents now. Maybe Jens, if you want to start, or Markus.
Yeah, maybe I continue here. So a fundamental disadvantage, I think, or challenge in contrast to grid-based method is the numerical robustness when it comes to computing the spatial derivatives, and there, like the different branches of SPH and other particle methods vary a lot. So I would call it not disadvantage, I would call it challenge. Mm-hmm. As similar to when you say what is the advantage of particle-based methods, everyone would say, I don't need a mesh, so I can just take my CAD model and compute them directly on the CAD model and do not need to transform this model into a computational mesh. Yeah, but of course this is also can be seen as a challenge there, and there are very sophisticated algorithms out there which allow you automatic remeshing and everything. But of course this all comes at a cost. So if you want to say what are the fundamental differences, is the one is discretizing the volume that needs to be computed in the particle-based approach these are, so we discretize the volume. We only compute where the volume is. We don't need to compute the whole simulation domain where the material is flowing through. This is an advantage. But of course, the numerics behind have been much longer tested and applied for different grid-based methods, be it finite volume, finite element method, whatever. So there are the differences. But at the end, we compare Eulerian approach versus Lagrangian approach, and there are, for either of these approaches, nice solutions. Yeah, but typically, when it comes to compute free surface flows, I would say the particle-based approach are more natural and have an advantage there.
Mm-hmm. Jens, do you want to add anything here, or do you want to directly talk about the parallelization aspect?
What I want to emphasize here is, and this is also part of the history actually of FIFTY2, is that the Eulerian methods, in comparison to Lagrangian methods, just as Markus mentioned, they had a head start in the research. So while SPH and other particle-based methods were kind of a niche method, whereas the Eulerian grid-based approaches were in the focus of the research. When we started our research at the university, so somewhere 2007, and for me somewhere 2012, we saw that those methods, so particle-based methods, they have some inherent properties which have a very high value for users of this method, such as that they do not rely on a grid, so you do have a very minimal post-processing. But there are also major workloads and challenges to solve. And this is why we focused on those. And nowadays with PreonLab, we do have a solution which overcomes those formal limitations and now brings particle-based methods to a level where it actually really can be used as a crucial and as a reliable part of numerical physical simulation.
Mm-hmm. Great, that's very well explained, guys. Thank you so much. What I also want to delve into is when we have, as engineers, the traditional methods, like let's say we use OpenFOAM for CFD, we have this kind of convergence criteria. Does this also exist in the SPH method, or what criteria do you use to tell if we approach the right solution? What would you say here?
So what I need to emphasize is that we always compute transient flows.
Mm-hmm.
So there's no steady flow. So and so then I think the convergent criterion question shifts a bit. Yeah. In contrast to other SPH solvers out there, we have an implicit formulation which like really solves for the Navier-Stokes equation. Mm-hmm. And in this formulation, there's a convergent criterion for every time step, of course, that tells the solver, yeah, okay, we met the criterion, which is like compression. So it's we can say, okay, that the volume does not compress, which is important for fluids, and this is in there, and this makes also our solution so much more robust than what is usually known as SPH solvers.
Mm-hmm. Jens, do you want to add anything here?
Exactly. So this was one thing we learned when we got in contact with the mechanical engineers. They told us, for example, they have an application which is a gearbox simulation, so sloshing of oil in a gearbox. And using Eulerian approaches, they encountered the problem that they initialize a specific amount of fluid, so specific volumes like 400 milliliters, for example. And throughout the physical time they're computing in this transient setup, they lose volume due to the numerical diffusion. And so what we learned is at this point that with a particle-based approach, solving for the compression, as Markus just said, we can ensure that no volume is lost throughout the physical time that is computed. And so this is an example where you can actually visually also see the result of the solver and the residual, which is the compression of the system which is solved.
Mm-hmm. That's great. What I also want to talk about is your solver per se. Markus mentioned PreonLab. Could you maybe explain for someone who's not familiar with SPH or the tool per se, what does PreonLab do? I mean, you use SPH method, that's for sure. How can an engineer use that? Or is it only for engineers or also other target customers?
Yeah, so PreonLab is a software suite. I would call it a software suite. So if you, as a researcher or as an engineer, if you have a great numerical approach, this will not help anybody because you need to make it available to the world. So you need to use it somehow. And PreonLab is a fully featured software suite. So you, if you own a license of PreonLab, you get the graphical user interface, which enables you to import all the necessary data like CAD models to specify where the fluid comes in, to specify kinematics like rotations of gears. So you can do all of that in the graphical user interface, also including all the post-processing, for example. So you can set it up. You can start in the GUI, so the simulation will run. You're able to monitor the simulation while it is running. So you see what is happening actually during the simulation. And after the simulation, you can perform all the post-processing, placing sensors in there, getting all the data that you need to obtain from the simulation and getting the actual insights from it. But it also includes a Python interface. So if you're interested in scripting, you can also use your Python text editor to script against the PreonLab API.
Mm-hmm.
And of course, also perform all the visualization aspects.
Yeah, that's what I also asked myself, because when I saw it on LinkedIn, like a very, very nice video, or also on YouTube, and I was asking myself, hey, was it done in Blender? But then I quickly learned, no, this is already integrated in your tool, which is really amazing. And which is also important, because if you talk to non-engineers, let's say engineers use your tool, but you talk to non-engineers and they want to have it visualized and they don't actually understand what's happening there. I think this is a crucial aspect, that you actually can show people what's going on in the simulation.
Yeah, exactly. So we think of PreonLab as a whole product for every stakeholder that is involved in the decision of a product design and product in general. So it serves engineers to understand what is going on a physical level, to do virtual engineering there, but also to convey their insights to their manager and to the designer by actually transporting not only graphs and red and blue and green colors, but also the real visual clues that the people understand, which makes meetings and virtual engineering more efficient only in our opinion, but also in the opinion of our customer. Yeah, this is not only eye candy; it's really an added value for our users, and we are very proud to say that not only CFD engineers are using our software, but also people really from the test bed that have these year-long experience and understand what you need to look at as a test engineer, and transform their knowledge now to the virtual world and save a lot of time and money by front-loading all these tests.
Mm-hmm. Yeah, that makes absolute sense. I also want to talk about the parallelization aspect. So you can not only run it on one CPU, you can run it on multiple cores, if I'm not completely mistaken here. Jens, do you want to talk about this parallelization aspect and also how the load is distributed between the cores? That's very interesting, I think.
Yeah, so in the very early days, we started with an implementation working on a single workstation only. But even though our method really is very fast and solves for the engineering problems very fast, we of course understood that even faster is even better, and that more hardware can solve for this problem. So we started working on an implementation of a distributed computation using our method and using PreonLab, which is not trivial, using a particle-based approach, since you do not have this uniform grid where you can then do a domain decomposition, so take part of the space actually and distribute it to a specific node in your HPC cluster, because particles can move freely in the entire domain. So they can actually could move from one part of the domain to the other, and therefore to another node. And what we have implemented in PreonLab is a so-called hybrid MPI approach, which means that the MPI interface, so the MPI communication, is only happening in between the nodes and not for single cores. So on each and every node, the implementation works on a shared memory system, reducing the bottleneck of the internode communication, while the internode communication only happens where it is really necessary, so in between the actual nodes. And furthermore, of course, this also makes it necessary to distribute the workload to the nodes as good as possible, especially because we learned that many of our customers have pretty heterogeneous MPI clusters, so not every node is as powerful as the other node. And therefore, we have a load balancer, which after every simulation step, or after every X simulation step, checks for the performance and improves the distribution of the workloads in order to make the best out of the hardware that is possible.
Mm-hmm. On another note here, so in our DNA of the company, so we started as a researcher, as a computer scientist, and computer scientists want to make things faster and more efficient. And so here in the field of SPH simulation, we had like the best playing field that you can imagine from this perspective. So when I started, we were excited about being able to simulate like 100,000 particles which were computed in 1 week, and but we were very proud of it. Now we have customers doing their own simulations for, you can see on our homepage, water weighting by Volvo, which they use 150 million particles, and is simulated in a shorter time than this 1 week. I think it's like in 2 days or so. And this is only possible by our highly talented team of high-performance computing specialists, which are fighting for every millisecond. But still, I think so that PreonLab is very fast, and it is seen by our customers, which are doing benchmarks and comparing PreonLab to other software. They say, I cannot believe that it's that fast, so there must be something wrong in the computational result, because you're cheating here probably. Mm-hmm. But still, I think that we will see a lot of progress in upcoming years there. And so I often compare it to like changing the simulation world from the same experience that computer science went through, from programming with like these cards, and you needed to you got the results days after it, and you saw, okay, there was something wrong in my code, and now how efficient can we compute and write computer programs now. And I hope, and we are fighting for that this will change in the same way for the simulation industry.
No, I think you two really explain it in a very enthusiastic way. Now, I can't wait to maybe one day test your tool. It would be really awesome to do so. When it comes to validation, I'm sorry if I'm asking this question again. I'm sure there is not this kind of convergence thing that we discussed. But how do you validate such a tool? What are the techniques that you use? I mean, for FEA, there's this common patch test. For CFD, there's maybe something like this famous backward-facing step. What is this one validation case or validation cases in SPH that someone can use to see if the tool is really giving valid results?
Okay, so maybe interestingly, so we have 3 pillars at FIFTY2 where which are the main focus of our work, which should help us to realize what we aim for, which is usability. We have covered it. So PreonLab is an all-in-one tool. We have efficiency, which is the other pillar. And the third pillar is reliability. So there we focus on validation and, of course, making the software robust, because with every change, and we are progressing or developing it in a rapid pace, there's always the chance to introduce regression to the code, right? And so reliability is very important. We have a lot of different a big test suite which is growing. And finally, now your question goes to how do you validate this code? And this was always a long question, because where PreonLab or particle flows in general are very good, which I mentioned earlier, is in free surface flow computation. Now go and find what the literature says about free surface flows. So the most cases are internal flows that you will find from a CFD point of view. And for free surface flows, and especially when it comes to not pressure-driven flows, but flows that are showing microfluidic behavior, there you won't find that many. I just saw recently that you posted something about the Torricelli case or Bernoulli case. This is one of our validation cases. There you can really analytically pre-compute what the solution should be. This is tested, but this is pressure-driven flow. And then there are a lot of, we have oscillation droplet to see that the frequency which a droplet would oscillate in space is really matched by our cohesion model. Then we have this famous marine dam break example, which is also pressure-driven flow, where they have also pressure forces that are measured in the real experiment. This we have also publication on. And then there are a lot of customer-driven validation cases where the customer did some really they put some effort in to build up a benchmark for free surface flow computation for water, especially because they don't find much in the literature. So very often we face that the customer has their own set of benchmarks, which are either really related to the application or just on a more general level. If you go to our homepage, you find something where we have a flow coming, an impinging jet, and then this hydraulic pressure jump is on the top, and then there's a flow running down a plate which is inclined, and there are cylinders on the bottom which the customer measured what the simulation predicts and what the experiment says, and there we are in very good agreement. And this is one now of our test benchmarks as well.
Very
but it was a lot of work that we and our customer put in to build up this validation suite.
Got it. When it comes to the licensing per se, how does it actually work? Can I buy an annual license for PreonLab?
Exactly. So in general, the license is purchased on a lease base, so as an annual license. So it includes, as I mentioned before, it includes all the aspects you need for the work with PreonLab. So there are no modules or something like this, but if you license it, you get it all, and you can do all that can be done with PreonLab. Of course, there's also some special licensing for MPI capability, for example. And in general, we are, of course, also interested in getting in touch with universities. So we have, of course, a special program for academic licenses, which can be applied if somebody is interested in using PreonLab, for example, in the scope of a lecture.
That's super cool. Maybe I can test it on my channel in the future and show people how it's actually used and what it's capable of, because you have some videos on your channel, which I'll definitely link down in the description. And it's really amazing to see what you can do with your tool. It's so cool. Do you look for people in the field of computer science or engineering?
Absolutely, yeah. So we founded in 2015, and we grew now to a size of 25 people working at our headquarters in Freiburg. But we still are looking for people who want to work in the field of engineering and in specific at 52. And so there are a couple of vacancies. So of course we are looking for software developers. But we also have mechanical engineers working at 52, making sure that everything that is developed is in close contact and is in relation to the actual application of our customers.
You also probably have the recruiting page on your website, so I'll link that anyway down in the description as well. If people want to reach out to you in particular, how can they do that?
So in general, please do not hesitate to follow us on LinkedIn. So this is our most important channel to provide information, of course, besides the website. So if you want to reach out for us, go to the website, write an email, or contact us via LinkedIn.
Mm-hmm. And I will link your profiles as well down in the description. Any last motivating words, especially for people who heard from SPH the first time, or maybe want to delve into SPH but are a little bit demotivated? Because I think, from what I've seen a lot of social media, is that a lot of people use OpenFOAM and other tools. But I think SPH is very promising. What would you tell them if they want to delve into SPH? Or
yeah, in general, if you're interested in SPH and you want to see SPH done right, then PreonLab is the right choice. And it is not only a great method for specific applications and to solve specific problems, but with PreonLab it also comes in a really nice and usable tool which you will love to use. So and it will also make you start testing things and trying out things that you might not would have tried out before.
Mm-hmm. Excellent. Markus, anything else from your side?
Yeah, so we are very open to launch academia programs or at universities. So if someone is listening who has the responsibility to introduce PreonLab or SPH in his class, so we are in cooperation with the Karlsruhe Institute of Technology. This should be launched. Actually, we're discussing about it, and I hope other universities will follow, such that young engineers and researchers get in touch with, as Jens said, SPH done right. So I think now PreonLab is in the industry for 5 years. It's a proven method. It's not only applied in automotive industry, which is our main industry, but also we have customers in the field of white goods, so applying it since years now for optimizing dishwashers and washing machines and whatnot. So and even on large scale simulations are possible, and this is possible without a lot of knowledge required from a user side. So you will learn it very fast, and you will have fun using it. So this is also one of our main goals, like that work should be fun, and if your work is in the field of virtual prototyping or virtual testing, then the tools that you're using should be fun and not a pain.
Yeah, absolutely. I agree here. And I really loved talking to you guys, and it was really in the way you delivered it in an enthusiastic way. I really enjoyed that for sure. And before we wrap things up, I also have to mention that you can, in PreonLab, if I'm not mistaken, put something in like sensors, like in different places, which you then can measure for your result control, if I'm not mistaken, if that's correct, right?
Absolutely, yeah, for sure. It's an engineering tool, and you need to have virtual sensors. You can place them while the simulation is running. You can add them in a post-processing step so you don't need to have put a lot of brain power in there before you're running a simulation. Very often it's the case that you will be surprised by the outcome of the simulation, that you would want to have a control sensor at another region that you originally thought, and this is absolutely possible in a post-processing step. And we provide a variety of sensors that were of course requested by our big user base now.
Wonderful tool. So with that being said, guys, again, thank you so much for your time. And I'll link everything down in the description and overlay some nice visuals, images or videos during this podcast when I upload it. And thank you so much again. I hope to see you maybe in a second part in the future.
Yeah, thank you. It was nice talking to you, and you're welcome to test PreonLab anytime.
Thank you so much.
Thank you very much. Yeah.